Hello everyone, we are Group 4 from Mechanical Engineering Design 1. I'm George and my teammates are Havva and Azra. Our senior design project is Agri-Bot, a solar-supported agricultural spraying robot. The goal of this project is to improve safety and efficiency in pesticide application by enabling remote operation through a web-based control interface. The main objective of this project was to design and develop a solar-powered, solar-supported agricultural spraying robot. Our goal was to reduce direct human exposure to pesticide by enabling remote and wireless operation. In addition, we aim to create a user-friendly web-based control interface that allows intuitive control of the robot through a mobile device. From a mechanical perspective, we focused on developing a modular and lightweight structure that could be easily assembled and adapted. Finally, the system was designed using low-cost and accessible components to ensure practicality and scalability for small-scale agricultural applications. To achieve these objectives, we designed the system architecture and mechanical components, which will be presented next.
Here are the main components of our design. First, we have the spraying system, which involves 12-volt pressure pump, two nozzles, two nozzle holders, inline filter, hose clamps, 2-liter tank, and slush foam, and epoxy glue. For the next system, we have the drive system. We have used the FIT 0441 brushless DC motor with encoders embedded in it. We are using 4 driving wheels, mounting hardware, Sigma profiles, and plexiglass sheet. Here we have the control and electronics components. We are using the Arduino R4 Wi-Fi module. We have a buck converter, relay module, and a mobile phone to reach the mobile interface. Next, we have the power and solar components. We are using 2 solar panels and a 12-volt battery pack. Our motor involves an FG outlet for the encoder, and for future work we can use the FG outlet to use odometry. Here are our CAD models. We have our first model, which we have gathered, and the second one we used for the motion analysis.
And the physical behavior of the system was simplified and represented using basic force, torque, and inelastic relations, and then solved numerically using ANSYS. For the technical analysis, we select 3 critical components of the system, and the first one is the motor-to-wheel connection rod, which directly transfers the motor torque to the wheel, and its materials is structural steel, and the load case is the motor torque and the weight of the robot. And the second crucial component is the base plate, which carries the weight of the system components. Its material is plexiglass, and we apply load as distributed and fixed support at both locations. The third component analysis is the motor holder, which supports the motor and transfers load to the base plate. And its material is PLA. It is 3D printed, and we apply motor weight and as a surface space and motor torque. And overall, the analysis confirms that the selected materials and geometries are appropriate, and the critical components remain within the safe stress and deformation limits under the static loading conditions. And these screenshots are taken from the stress results. And this is our torque calculations. And while the torque was calculated analytically, the motion analysis was performed using a prescribed rotation to demonstrate the wheel's kinematic behavior.
The robot is able to move forward, backward, and turn smoothly while maintaining stability. Liquid-induced oscillations are attenuated by using internal anti-slush foam. Epoxy was applied to increase sealing and prevent leakage. The spraying mechanism operates simultaneously with the motion, demonstrating that mechanical, electrical, and control subsystems work together as intended. The system is controlled wirelessly through a web-based interface, allowing real-time user input without any physical connection. Overall, these results confirm that our design goals were successfully achieved and that the prototype performs reliably as a functional agricultural spraying robot.
In conclusion, we successfully designed and built a fully functional solar-supported agricultural spraying robot. All major system components, including the mechanical structure, control system, and spraying mechanism, were successfully integrated into a working prototype. As future work, the system can be further improved by integrating autonomous navigation and sensing capabilities, as well as enhancing energy efficiency and adaptability for real agricultural field conditions. In addition, the solar-powered system can be optimized through improved panel placement, energy management strategies, and the integration of higher efficiency solar modules to enable longer autonomous operation. Thanks for listening.